So today is the second lecture of this series on type systems, and I will continue discussing the C structures today. Let me first try to remind a few things which we have done last time. So we gave a definition of a C structure as a category, as a set-level category equipped with some additional quasi-algebraic structure. We defined some related constructions which I will remind in more detail in a moment, in particular some notations. Then, given any C structure C, we said that there are two graded sets. There is B of C and B tilde of C, where this is just the set of objects of C graded by the length with respect to this length function which exists on the set of objects. And this is the set of sections of the canonical, of the display maps, of the canonical projections. So this is the set of pairs of the form X projects to the father of X by the canonical map P of X. And the elements of this thing are triples of this form, where S is a section and X is in Bn. So no, Bn plus 1. Thank you. Here also Bn plus 1. Yeah, please correct me, because this little indices, numerical indices under all the sets, always confuse. I mean, I always make mistakes in them. The father of the point is the point itself, and
is that reasonable, or could us when the cell that father is only defined and the length is strictly bigger than 0?
One can say that also. I mean, yeah.
But you have many exceptions if X is not a form.
Right. Yeah. One more exception is not much of a problem, right? Now there was one, essentially one somewhat non-trivial statement proved, and I will reproduce it. But before reproducing it, I'll remind a few notations. The main notation which we want comes from the main. There are like 4 notations, but they all come from 2 diagrams, which look like that. X. X, I of X, so if I build such a square, if I build such a diagram by here looking at a sequence of canonical projections, here to the canonical projection, and then building the canonical square on every step by step, then the object which one obtains here, which depends entirely on X and Y, but it depends only on X and Y, on nothing else, and on I, excuse me, is denoted P Y upper star X comma I. So that's an operation on these sets. That's a partially defined operation here. Now, if I have a section here, I can pull it back relative to this map, and I'll get a section here which is called Py upper star S comma I, which is also which is defined entirely by S and by Y. So that's a partial operation which takes an element from one of these sets, an element from one of these sets, and returns an element from one of these sets. Now I can draw the same kind of a diagram or maybe that should be R. Now suppose that instead of taking, excuse me, instead of taking a canonical projection from Y to here, I take one of the sections of the canonical projection. So the canonical projection itself would go here, and I take one of its sections as a horizontal arrow. Py should start at Y, right? So it's yeah. So Y should not be even here. That should be some. Well, it can be Y, but it's not. It's not an argument of the. Right. So it's P F T I X actually. So it's the same picture, except that now here I'm considering one of the sections instead of the canonical projection. So then the object here is denoted R upper star of X comma I. And if I had the section here, then the pullback of this section will be R upper star of S comma I. Now the first construction takes as an input a section and an object. So it's again a mixed operation, an element from here and an element from here, and returns an element from here, excuse me. And the last one takes two sections and returns a section. So we have four partial operations which can be their sort of signature is of the form B times B to B for the first one, B times B tilde to B tilde for the second one, B tilde times B to B for the third one, and B tilde times B tilde to B tilde for the fourth one. And I call this, so these operations, in fact, one needs to put indices here, but let's ignore the small indices for now. So it's, in fact, each of these is not an individual operation, but a family of operations which are parameterized by three natural numbers, satisfying some inequalities. So sometimes it gets a little confusing, but so this is called T. This is called T tilde. This is called S. This is called S tilde. Yes, and there is another operation which we have considered, and that was operation delta, which goes. So let me also draw the diagram before. For writing it may be here. So if I have x going to ft of x by p of x, and here I also have x going by p of x to ft of x, I can take here px upper star of x, and then here I'll have a diagonal section. But I'll use little delta for that. That's also an operation. It takes an object, it takes an element from B, and returns an element from B tilde. So that's the fifth operation, which is delta from B to B tilde.
We might
We theoretically speaking, we don't, but in practice, the first argument is y. So no, the first argument is so the idea is that here it's ft g d, and that remains that removes the ambiguity. So this is the fiber product, in fact, because it's a partially defined operation. So it's a map from the fiber product. So it's a fiber product of B with some index, with B with some index over something, and in that case it's over also B with some index, and the condition being that the father of the first argument is iterated father of the second argument. And here the father of the first is iterated father of the source of the target of the second argument, and here this is D and D, and so that D is, excuse me, let me write these things here too. So there is D from B tilde to B, which just takes S and maps to X.
So it's the target.
It's the target, yeah, and then you can take the father and obtain the source. And then there is Ft, which was our starting so essentially let me just check that I didn't forget any operation. Yeah, that's all. These are all the operations which I want to consider. And what we have proved in that proposition was that in fact, there was some trick which I don't quite remember now, and we didn't reconstruct it last time either, which I think shows that these two operations can be reconstructed from these two operations. Let me have a look here. Yes, but why there is at least one arrow? One somehow needs to use delta, I think, for that. Because one needs to have a section to get started with. So one uses the delta section. Well, let's try to reconstruct it just for the fun of it. What might be 0? No, when I is 0, it's not particularly interesting because I is 0 means that this is just X itself, and then the operation is identity. So, no, but the issue is that there can be X's for which there are no sections at all. and also it's non-constructive to say let's pick a section. And so there is a different construction. Let's try to reinvent it. I don't have it for some reason in my notes. So what one needs somehow to use is this. So let's say we have x ftI x y, and we want to define this pullback using only that. So this is ft x. I think the way it goes is something like that. So here I have px upper star x. Here I have delta x. Now I can take the py upper star of delta x I plus 1. And then d of it will be, this will be d of py upper star delta x I plus 1 equals this. And so the father of that, I mean equals, sorry, what did I say? So anyway, so the formula is father of d of py upper star delta y I plus 1 equals py upper star xi. So that's the formula. And that formula shows that these operations in principle can be deduced from the remaining actually need all of the remaining operations to deduce this too. So the proposition which we had stated that if I have a contextual structure C and I have a family of subsets Bn prime in Bn C and Bn tilde prime in Bn tilde C, then this, first of all, these subsets, so that these subsets correspond to a contextual substructure if and only if they're closed under these operations. That was the meaning of that was the proposition. And moreover, the contextual substructure corresponding to such subsets is unique. So any two contextual substructures for which these subsets coincide are the same. So, so there is a bijection between contextual substructures of C and families of subsets in B and B tilde of C, which are closed under these operations. So now I'll draw a very big diagram. So this suggests that C can somehow be reconstructed from B and B tilde in these operations. So that there is an alternative axiomatics of C structures for which types now are not objects and morphisms in the category, but sorts, I mean, are not morphisms and objects in the category, but this B ends and B tilde ends. And operations are not categorical operations or whatever C structure operations we had, but these operations. And I'll just outline one construction. I'll see how much detail I want to go in it. So it is indeed true I'm still not completely sure I have a full list of axioms on these operations, which is equivalent to the axioms of the contextual structure, of C structure. But that shouldn't be difficult to work out. I mean, so the kind of, maybe I should mention what kind of axioms one gets. One gets axioms of the sort, like, what is the father of T of something, for example?
You remember the length function too, or no?
Yes, the length function. Yes, but the length function is now embedded into the fact that we have infinitely many sorts. I was just ignoring the indices here, but in fact, one has to write for every n, m, I. So the sorts of the new series, the sorts will be bn for and bn b tilde n plus 1 for all n greater or equal to 0. And then the length function is just the grading function if you want to take them all together. Okay, now where's my favorite diagram? Hmm?
Is the point of what you're doing to get an algebraic theory?
No, the point is what I'm doing is to get closer to the syntactic type theory. And we'll see that in this description, it corresponds very, very closely to the syntax of type theory, unlike the original description of C structure. So the correspondence between this description and syntax is much, much more straightforward than the correspondence between the original description and syntax.
So maybe this is sort of the same what he was asking, but can one see this as saying we're getting a new set of operations which could alternatively have been used to describe the same essentially algebraic theory?
Yes, that's exactly, yeah. That's exactly what we're doing, yeah. It's like describing, I don't know, groups through product and division, for example, or like describing groups through division or through product and inverse. That's a similar kind of a thing, except in a more kind of complicated version of it. So to go further, I want to draw one diagram to show, to explain the following. So there is only one. The first issue, when one wants to reconstruct from this, the C itself, so we already have the set of objects of C. It's just the union of all the BNs. But we need morphisms. So let's see how can we define what is the set of morphisms x, y, where x is in Bn and y is in Bm, purely in terms of these sets and these operations. And I'll start with this by assuming that there is a contextual category already, contextual structure already, so they're already morphisms. And just let me draw a diagram. It will be a big diagram, and then so one considers the case when in this diagram one considers. Sorry, let me see how to do it better. Maybe first something simpler. So description of a morphism in terms of these elements of this set is complicated. The complexity of the description grows quadratically in n, more or less. Well, the size of the diagram grows quadratically in n. If you, yeah, I think so. Well, we'll see. No, the induction on M is when y is right, but the induction on am I saying the wrong thing? Let me try to draw it in the case when, oh, maybe I'm mixing n and m here. X is n. Oh, right. You're totally right. It's my notation here. It's yx. That's and x is in x is in Bm and y is in Bn. And then yes, and then it's by m. So let's see. Suppose that for m equals 0, as Pierre just noted, x is the final point and so final object, and then there is just one morphism, and there is nothing much to describe. So suppose, for example, x is in B3. And let's try to see how we can build a morphism. Or maybe let's start with B1. So here I have x. The father of x is the point. And here I have y. Because it's the point, I have here a canonical map Py. No, not Py. I have here the canonical map. And then I have a morphism F. So how to describe it? I can. So this thing is P. So if y is in B n, then this is Py n. I think we denoted it like that. So the projection to the point is always the composition of the canonical morphisms. So I can take Py n upper star of x. This this filling of this square defines the section S of f, and then f is completely determined by this section. So f itself is just a composition of this section with this map, and this map is well, so far we do have a category, so it's determined by this section. So in that case, x in B1, we have that more and m n1 yx is a subset in B tilde. Let's see, so if x was in 1, then this will be in 2. It will be B tilde 2.
There's a subtle shift of notation here with the
Oops.
integer now being a subscript rather than a second, right? Are there two notations?
In here, no, but this is different notation. This refers to the tower on the right, and this is just this is the lower map is different now than rather than horizontal map is a composition rather than the vertical map.
Wouldn't it be for the n+1 when it depend on y?
Yes, you're right. N+1. So it's subset in here. And one can explicitly say which subset. It's the subset of, so it's a set of S in B tilde n+1 such that, now let's see what the condition should be. I suppose just such that g of S is Py n upper star of x. And this is completely in terms of our operations. This is the iterated t. It's t iterated n times. Now, when one has x of length 2, let me write it this way. Basically, the idea is to say that, so if one looks at this, then one actually sees a little more than the case when ft of x is a point, more than the case of x in B1. What this simple diagram shows is that f is completely determined by its composition with the canonical projection here, so which I call the father of f. By the way, this is not right. There is something funny here. Just a second. No, this is not this. I'm sorry. Okay. It was right in the case when x was in 1. But now suppose that x is not in 1. Suppose that the length of x is greater than 1. Then this is not anymore the canonical projection, but this is some sort of a map. And I can call it father of f. And then what I get is that f is completely reconstructible from the s of f and the father of f. And the father of f is a map from y to x, which lies in on one grade lower. So inductively, I just define, I can inductively now define morphisms as a subset in a certain iterated product of this B tildes with some kind of conditions like that. Now one can write the composition of morphisms in these terms. It's a bit of a, it would be hard on our blackboard, but otherwise it's doable. And all of the constructions, all of the structures of a C structure, all those pullbacks and everything, they all can easily be written in these terms using only these operations. So that's an unfinished proof that that we have indeed an equivalence of two quasi-algebraic theories: the original C structure theory and this theory, which I call the sequent notation for the for C structures, because we'll see that these things are exactly sequence. Yes.
With your previous remark, so this is an abstract formulation of saying that the context morphisms are basically tuples of terms of appropriate type.
Yes, of course. Yep. So actually, at the end, this description can be probably more compact than the original one. If one writes the original one line by line, like honestly opening up all the definitions, like pullback square and all of that, then it might turn out that this is shorter, because what one actually has is like not so many operations, and the actions are rather simple. At least it's not particularly longer. So the next topic, which is which I need to present in more detail probably, or it is so this is, I'm sorry, I still haven't posted this extended version of my notes on the wiki, and so what I'm going to be talking about right now is not in the old version of the notes. I really need myself to make myself to do it today, so I'll I'll try. So we're going to define the notion of equality structure on a C structure. Now, what is that? This is about the following. Suppose we have a C structure. So it is a quasi-algebraic theory, of course. So suppose I have a collection of equivalence relations on all of B's and B tildes, which are compatible with these maps. And then I should be able to define a quotient just because of the existence of free objects. And so, but in quasi-algebraic theories, quotients tend to increase the size of an object very much. So because, for example, if I take a category which consists of two objects connected by an arrow and consider it as a quasi-algebraic theory, and now take a quotient of it by identifying these two objects. As a consequence, I get an infinite number of morphisms in it, because now I can compose this morphism with itself. So the projection from the original object to the quotient object is, in most cases, not surjective. And this quotient object can be, like here we go from very finite to an infinite. So it can be much bigger than the original one.
So the quotient in some categorical sense, the universal object with the
Yes.
categorical quotient.
I think the trick is the same as for making a free object. One considers all the objects of this sort to which there is a homomorphism which respects the equivalence relation. One takes the product of all these morphisms, and in this product one takes the intersection of all the sub-objects containing the image. And then one gets this thing. So in practice, and especially in type theory, and it's important to have some class of equivalence relations for which one can guarantee that the projection is surjective. And one such class is what I call equality structure. So equality structure is a collection of equivalence relations. So one starts with a C structure in the sequent notation. And then one considers equivalence relations on Bn's and B tilde n's, which satisfy a rather long list of conditions. And then one proves that provided that these conditions are essentially are almost necessary and sufficient for the projection to the quotient to be surjective. For the
You also want that the quotient is actually by sub-equivalence relation and not that it does not force a differential equality.
Yes, yes, which in that case does happen. Now there is one thing which I haven't finished and which we'll need to do in the formalization thing when I become a little bit more outgoing. I hope in the next few days we'll start working on it more in a more organized way. It's not immediately obvious that if one has a homomorphism of sequential structures, which is surjective on every sort, then the associated homomorphism of C structures is surjective on morphisms. because morphisms are made in some complicated way, and it's not immediately clear that that holds. So one of the things to verify, that was actually where I kind of stopped my writing, my last period of writing on this thing, is to verify that for an equality structure, the corresponding projection is also induces a surjection on the level of morphisms on the level of morphisms of C structure. Okay, so
This is a problem because when you like this definition of morphism, you have some equality sign, objects such as something, and they can be more things getting equal. That's why you.
yes, yes.
That gives some kind of product.
Yes, but so in practice, yeah, I'm saying it's not an obvious statement. One has to verify. In practice, this whole piece of the theory is something which I filled in this summer. And when I was writing it for the first time, I tried and failed to do it because it just doesn't. It's somewhat unnatural from a point of view of normal mathematician, the kind of constructions which one has to do there, and there are many axioms, but most of them should be easily verifiable. Obviously, for the type theory, what it means is that the equivalence relations in question will be the definitional equalities, context-dependent definitional equalities. And then what one will have to do one will have to verify that whole bunch of simple conditions on this equality judgments in order to make sure that the syntactic category actually is a good contextual category. But at least there will be a list. So.
Will you show us the connection between this, what we call sequence presentation, and a more familiar presentation of the type theory? Or are you assuming we already can recognize?
No. I'll give you very precise correspondence in the next as soon as we go to type series, which is probably better done next time, because just not to mix two things. So the next time, then I'll give a precise definition of a type theory in terms of contextual categories, and all these correspondences I'll outline. So let me just there are not that many. So one starts as following. So suppose let's see C. Well, I was using C here. So C equals B tilde F T D C S T tilde S tilde delta be a C structure in sequent notation. So a pre-equality structure on C is a collection of equivalence relations phi n in Bn times Bn and phi n tilde and Bn tilde times Bn tilde that's one, and then there is two. And 2 is for every x in B, an equivalence relation called like this on B of x. So B of x is the subset in B which consists of those elements whose father is x. So these are elements over x. And an equivalence relation well, I'll denote it by the same symbol, it shouldn't be confusing, on B tilde of x. So B tilde of x are those sections whose target is x. So this is just the intermediate technical concept. Will I what?
One more time with that last thing.
B tilde x. This is set of S in B tilde such that G of S equals x. It's just a tilde subscript x. Well, so they're on different sets. So I take the same notation, but they're on different sets, so there should be no problem in mixing them up. So these two additional equivalence relations correspond, if I remember correctly, to in this case of a type theory, B will consist of contexts. So the father is taking a context which, by dropping off the last type expression from the sequence. So B of x is the set of all contexts with the same first segment, but possibly different last segments. And this relation is well, actually, in the type theoretic case, I think this relation is identity. It's a little funny. Let me. Yeah, I think in the case of type theory, this is an identity, but somehow it was convenient to introduce it anyway. So we'll see later. This is more of a new material, so I don't myself remember how it all works together. So. Right. So the first construction, one needs to define a relation tilde n on Bn, and relation tilde n, also this notation, on B tilde n plus 1. I'm trying to give a definition of equality structure on a sequence. Equality structure on a C structure. I started with a. No, this is not the data for the equality structure yet. This is something called pre-equality structure. I need to do my definition in 2 steps. I first introduce a technical intermediate definition called pre-equality structure, which isn't good for anything at all, except for the certain construction which I'm going to do with it, which I'll then use in the definition of the equality structure. Yes. Yes. So given this collection of data, I now want to construct new equivalence relations, tilde n on Bn, and also tilde n on B tilde n. So let's see. So what we do is we do proceed by induction on n. So B1 equals B1 of the point. So we take tilde 1 to be equal to tilde point. B of the point. And then in general for x1, x2 in B n plus 1, one has x1 is equivalent n plus 1 x2 if the father of x1 is equivalent is n equivalent to the father of x2, and there exists x2 prime. Yeah, so this constructively this is not completely satisfying, but it can be constructive existence such that I'll draw a picture in a moment. Father of x2 prime equals father of x2 x1, x2 prime is in phi n plus 1, and x2 is tilde equivalent, x2 prime is tilde equivalent here is the father of x2 to x2. This, of course, is impossible to understand without drawing a picture. And the picture looks as follows. So I have x1 and I have x2. Now I have a projection from, so they live in Bn plus 1. I have a projection from Bn plus 1 to Bn, which maps x1 to the father of x1 and x2 to the father of x2. So my first condition is that this should be connected by the previous relation. And my second condition is that there exists a third object which has the same father as this one. So it's some kind of a guy sitting here, such that these two are connected by phi, right? And these two are connected over the father of x2. So I had one equivalence relation, which was this phi, which was everywhere, and a family of equivalence relations which were vertical, like family of equivalence relations in the fibers. So now I'm creating again equivalence relations in the whole whole set by kind of composing the two. And a priori, this is not yet an equivalence relation. This is just a relation. And so for the sections, one does a similar thing. For this, I'll just try to draw it. So one takes S1, S2 with G of S1, G of S2 should be equivalent relative to n. And then there should be S2 prime, which is horizontally through phi related to S1 and vertically related to S2. Now there is a definition of what is an equality structure. So an equality structure is a pre-equality structure which satisfies a bunch of conditions. Yeah, so let me, I think I remembered what it is in type theory. So in type theory, these things correspond to the equality judgments. So that would be the collection of all type expressions in context X. And the equivalence relation is distinguished generated by judgments of the form gamma turnstile A equals B in type. This is this. And this is the similar one for the objects. Now, as far as these things are concerned, I don't quite these are some additional equivalence relations on context. I need to have to remember what it is in the particular example. Or maybe it's just important for the proof, and one can actually start with only those. I need to have a look. I don't remember. The case of type theory, I don't remember well. Okay, I think probably I'll stop here because it's 1 to 12, and I'll give the axioms for the equality structure next time, and then the next time we'll move to type theories. Thank you. Yeah.